Okay, today we will look at surprisal values for performances that are based on the principles taught in the Hidden Structures online course. So this is where we look at 2 cycles, mirrored structures, and AMP structures. Okay, now if you've gone through my improv card magic series, this is one of the particular cases that we covered, namely packets of size 12. Okay, so if you've seen other videos on this channel, one of the narratives that we've used is the matching up of card values, or perhaps card colors, or card suits, or even pairs of cards that add to the same number. Okay, so there are a whole bunch of different categorical relations that we've looked at for these card pairing routines. So as you might imagine, today we will be focused on card values, since I have ace through 6 of clubs and ace through 6 of hearts. And as you can tell, they're certainly not in some orderly fashion as displayed here, right? Okay, so let's go ahead and I'll just gather these up. And so what we're going to do together is we're going to just mix these, and I'm going to give you a whole bunch of choices along the way, okay? So some of these choices will involve what's called the Klondike Shuffle, which is what this is right here, the Klondike Shuffle. Others will involve the LR Shuffle, the left-right shuffle. You remember that? And then others will involve a mange shuffle. This is where you go like over, under, over, under, over, under, over, under, over, under, over. Let's see, what else could we do? We could even do a 50% coating of the cards. That's where you just count out half of them and then drop the rest on top. Okay. We might deal into 3 piles. With random stacking. In fact, you want to tell me how you like these stacked right to left? Okay, that's very good. Should we do 4 piles? Sure. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Well, if you want to be thinking about how you'd like these stacked, left to right, left to right this time. So the opposite of the last time. Okay, that's fine. We can also do up jogs. Do you remember up jogs? Even or odd up jogs. How would you like these stacked? I'll just strip these out. You want that one on top or this one on? You want this one on top? Okay, that's very good. We can actually do a Pharaoh shuffle. Do you remember that? It's kind of a fun one. This is where you break the cards exactly in half, like this, and then you just perfectly interlace the cards. And it actually doesn't matter how you begin the interlacing, as long as you just perfectly interlace them. That's considered a Pharaoh shuffle. Okay? Would you like to do any more left-right, or deal into 3, or you'd like to deal into 6 piles? Oh, okay. Let's see, how should we do this? 1, 2, 3, 4, 5, 6. Just having a hard time fitting it on the screen here. Should we stack from left to right or right to left? Right to left? Okay. Okay, so this would have been on the far right. Excuse me, I'm dropping cards here, making a huge mess. Okay. Anything else that you'd like us to do, just to kind of scramble these a bit? You want another mange? Okay, that would be fine. This is that over, under, over. It's kind of a fun one. Okay. You want to cut the cards? Okay, I'll just set those down. And if you were here, you would just cut them wherever you want. That's just fine. It won't hurt anything. That's great. Okay. Well, let's go ahead. You want to deal into 6 again? 6 piles. Okay, how about if we deal into 6 piles and then we'll call it good, right? Because my fingers are starting to get tired. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I am tired. I don't know about you. In fact, let's just see where all of your choices have brought us. I mean, there were a lot of choices that you made, and you kept throwing me curveballs as well. So what do we have here for the first pair? Ooh, that's nice. Check that out. How did you do that? Let's see. Why don't we check this one? Whoa, 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 whoa. You got 2 pairs. There's no way you got others. Oh, a couple of aces? How in the world did you do that? Or should I say, how in the world are you doing it? There's no way. I can't believe it. How in the world did you match up all of these perfectly? You've got to either be the luckiest person on planet Earth or the best choice maker in the history of the universe. Okay, so that's what we're talking about today. Now, we're not necessarily talking about how I did this. We've been doing this kind of routine over and over in many, many varieties and many settings using these 3 primary structures: 2 cycles, mirrored structures, and AMP structures. Now, if you rewind the video and look at the cards as they were laid out, you will immediately recognize it was a 2 cycle. Now, it wasn't a 2 cycle exactly like this here, like ace, 2, 3, 4. These were reordered within each half consistently. Okay, so if you look at the original ordering, there was a pattern that repeated in card values, and then the same pattern repeated a second time. That is a 2 cycle, and it is just as legitimate as this pretty orderly one here. Okay, it's still a 2 cycle. It's a packet in which there's a pattern that repeats twice. Okay, that's all we're looking for. Okay, and then from there, I honestly don't remember everything we did, but I did a Charlier shuffle of this, so that preserves 2 cycles. Oh, and then I did a Klondike. Klondike converts a 2 cycle to a mirrored structure. I did an LR, and then I did a deal into 3, and then I think I did an up jog. All of those preserve mirrored structures, by the way. And then I dealt out into 4, random stacking left to right. And then I even did a Pharaoh in or out. It actually doesn't matter. Either one will preserve mirrored structures. What did we do from there? Oh, we did a mange that brought us back here. I thought we did 2 mange. Well, I may have missed 1 or 2 in our chain here. But the fact is, we were just, in fact, I don't even think we came down here. We did not even take advantage of AMP structures, which are really, really nice because you can randomly stack pairs and things like that. So we stayed up in this portion of our diagram, actually. We just kind of bounced back and forth between these 2, either stayed within 1 using a structure-preserving shuffle for that structure type. Same thing here, or we bounced around between the 2. And then I ended, before I did the final dealing, out into 6. Oh, by the way, when I dealt out into 6 piles, I was over here. And because 6 is a divisor of the packet size 12, dealing out into 6 piles in that way and stacking from left to right or right to left will preserve mirrored structures as well. So I guess I should mention that. But I eventually brought it back here by way of a mange. And I'm just remembering now that I also did a 50% coating, which takes you from here to here or from here to here. Okay, but anyway, eventually we ended over here, and I asked you, or I kind of claimed that you wanted me to deal it out into 6 piles one more time, which would be fine, and that's what we did. But because it was a 2 cycle, so just imagine it has a structure like this where there's a repeating pattern. When I go through and do 1, 2, 3, 4, 5, 6, and then deal out the next 6 cards, we'll be matching up the card values. So the little companion pairs will all be matched up in those 6 pairs of cards on the table. Okay, so we could have gone on mixing and doing crazy things, but that's not the point of this video. The point of this video is to calculate Surprisal values, okay? But I just wanted to essentially surprise you with a routine because now we're going to calculate Surprisal values. Okay, and so we're going to attach a numerical quantity to what we call surprise. Or in the language of information theory, it's called surprisal. Okay, so that's what we're going to do today. So let's take a look at our Desmos activity, which can also be found in the description below of this video. Okay, so today we're looking at matching values. And in the next video after this one, we'll be looking at matching colors instead. Okay, so let's set the stage here. So given a packet of 2n cards, so n in the case of n in the case of this one here is 6, of course. Find the probability in Surprisal of producing 6 pairs, n pairs of matching cards after, quote, thoroughly mixing the packet. Now, in the mind of the spectator, who's not aware of the many powerful principles taught in my Hidden Structures course, they have no reason to believe that the cards aren't sufficiently mixed because they're watching you and you are giving them essential choices as to how things are done, how things are stacked, what's done next, and so forth. Okay? So for 99% of the spectators out there, they would agree with the statement, yeah, those cards were mixed well enough. In fact, we mixed them for so long that I was kind of falling asleep, actually. So yeah, they're mixed up. And then I have a note here. Matching cards could have the same color, or value, or suit, or parity. They could both be even-valued cards or odd-valued cards. They could add up to the same number. I could have had all of them add up to 17 or something. Or they could be of the same kind relative to a number card versus a face card. Or, in fact, any relationship that is known by the performer and can accurately be predicted ahead of time. Notation. We can represent the general situation by considering the following multiset, 1, 1, 2, 2, up to n, where identical values are nonetheless distinguishable. Okay? So in mathematics, most of the viewers probably are not accustomed to working with multisets. So this is where we're allowing a particular value to be listed more than once. Here, each one's being listed twice. But nonetheless, we are viewing them as distinguishable, just as mentioned here. Now, these all look identical. That one looks identical to that one. Well, that's true. It's just that when we go to do what we're going to do with these cards, of course, ace will be a 1, right? Here are, quote, 2 cards that have value 1, okay? But they are distinguishable. In other words, they are distinct. These are distinct cards, right? Okay, so that's all that's saying there. The probability, and consequently, the surprisal of randomly producing a 2-cycle, its corresponding mirrored structure, and its corresponding AMP structure are all equal to each other. So essentially, by chance alone, if you have cards such as we had here, ace through 6 of 2 different colors, and if you were to just randomly mix these up and find that they constitute a 2-cycle, the probability of achieving that is the same thing as mixing those up and achieving any one of these other structures. So from a probabilistic point of view, all 3 of these are equally likely. Now, of course, they're not very likely to begin with, very small probabilities that you would achieve one of these by just randomly mixing the cards, of course. But regarding their individual probabilities, they are the same, despite the fact that they're small. And then I go on to say, in fact, the above is true for any structure that enables the performer to perfectly pair up all of the matching values. Okay, so let's take a look at a Desmos idiosyncrasy. Although each of the functions used in this activity only makes sense for discrete values of x, Desmos uses a generalized factorial function, the gamma function, to draw a continuous graph that connects the corresponding discrete points in the plane. So technically, when we get to our graphs, it's really only the dots that correspond to packets of cards that can actually be formed in the way that we're forming them here. Okay, Desmos is using the gamma function to connect these in a nice, smooth, continuous way. Without loss of generality, we can determine the probability of producing matching values in this multiset after thorough randomization has been performed by analyzing a two-cycle structure of these values. Okay, so what I'm saying here is, since each of these individually have identical probabilities of occurring by chance alone, so to find the common probability for each of these, we can just find the probability of any one of these. So we're going to work with two cycles, okay? To do this, we will calculate the number of distinct two cycles consisting of these 2x values. Okay, so let me just try to explain this to you here. Why don't we do it in the case of 6, because that's what I've been demonstrating to you here. All we need for this is something called the fundamental counting principle. It's also called the multiplication principle. Okay, so that's another name. Okay, so I have 6 little slots there, and then I'm going to draw a vertical bar, which just marks the center of the two cycle. That's all I'm doing here. 4, 5, 6. Okay. Well, think about it. What can go into, well, let's start at the very beginning. So we have these, we have technically in our proof there in Desmos, we have like a 1, 1, a 2, 2, all the way up to a 6, 6. Okay. So these are like a red ace, black ace, red 2, black 2, and so forth. So how many of these values can actually occupy the first slot? Well, any one of them. You can start with any card at the beginning as we build up our two cycle. Well, how many options do we have here? We have 12 distinct values. So you would just write 12 right there. Okay. Now that's going to be multiplied. I'm going to put an x here for multiplication, so don't get confused with the variable x over there. Okay, x multiplication on my paper. Okay, well, how many choices do we have for the second position? And why is it not 11? So just think about it. So the moment you put one of these, like right there, what do you know has to go over here if it's going to be a two cycle? So let's say you happen to put a 5 of hearts over here. You just set that, that's the first one you happen to choose. What has to go over here? The 5 of clubs, right? It's going to be a two cycle. Okay, so there's only one choice actually for that position there. It has to be the companion to the one that we've put down, okay? Well, that affects how many choices we have then for the second slot. We can't use the card, the 5 of hearts that we just put down, and we can't use the 5 of clubs because it's headed over there. How many do we have left to choose from? Well, 12 minus 2 is 10. We have 10 left, right? Okay, now once this card is down, its companion has to go over here, right? And as you might reason, we can't use this one now or that one, so it decreases the number of options by 2 again. So this will be 8, and then the pattern just, continues. 6, 4, 2, would actually have 2 options at the end, because what would happen at the end is you would have like a 3 and 3 left. 3 of clubs, 3 of hearts. Well, any one of those can go there, and then the other one has to go on that last slot. Okay, but over here, all of these, there's only one choice for all of these. Okay, so if we go ahead and use the fundamental counting principle, we get the product. 12 times 10 times 8 times 6 times 4 times 2. If it makes you feel good, you could do times 1. May not be a bad idea for what's coming next. Well, come to think of it, actually, we don't want the 1 there. It's going to muddle us up. I mean, it's not wrong to have there because we have 1, 2, 3, 4, 5, 6. Okay, so all of the other ones are just 1s. So, in fact, let's go ahead and drop that, which I do in the proof and the Desmos activity there. And so this product of 1s won't change anything here. So this gives you the correct answer. Now, what do you notice about all of these? Do they have a common factor within each of these factors? Well, they do, right? 12 is equal to 2 times 6, right? And then what about 10? 10 is equal to 2 times 5. 8. 8 is equal to 2 times 4, right? And then, of course, 4 is equal to 2 times 2. And finally, 2, of course, can be written as 2 times 1. Okay? So all I have done is I've just factored out 2 from each of the factors in that string of 6 numbers. Okay? Well, what does that allow you to do? How many factors of 2 do I have? 1, 2, 3, 4, 5. So it's 2 to the 5th times what? 6 times 5 times 4 times 3 times 2 times 1. And I imagine you know what this is. That's 6 factorial. Okay, so the answer is it's 2 to the 5th times 6 factorial. Okay, so can you see how we could generalize this given 2x values? So essentially you have like x positions over here, x number of, instead of 6 positions, you have x number of positions here and x number of positions here. So does all of this make sense so far? I certainly hope not, because a mistake was made. I noticed it because our general formula doesn't agree with this one. Can you see where I made a mistake? So this is 12, 10, 8, 6. Sorry about that. We left off one of the factors. And so this little guy here becomes a 6. Okay, and now you're probably feeling, let me just cross this out, probably feeling a little better about the world because now the world is looking far more aesthetically pleasing than it did just a moment ago. The fact that the exponent of 2 matches the factorial is wonderful. Okay, so sorry about my omission. In the general case, we get this. Whatever the number of elements you have in each half of your 2 cycle, and here we're letting it be denoted by the variable x in the Desmos activity, it's 2 to the x times x factorial. Okay. Well, Desmos is wonderful. Once you have a formula, now you can generate tables and graph things. And in fact, that's all really that is done here. If we go ahead and turn this on. Now this is going to shoot straight up, by the way. Okay, let me just make sure you saw that. Okay, so it's the red one there. Too many red ones. It's red one without the dots. Okay, so this is what this is doing is as x gets bigger and bigger, x is 6 in our case, this is counting the number of 2 cycles that can be formed given the constraints that we've been working with here, where we have these pairs of values that need to be matched up relative to position, right? Okay, so that gives you the total number of 2 cycles that you can actually form from those cards that I had laid out, right? The 12 cards, ace of clubs through the ace of hearts. Okay, so all of the different ways. And I guess we could figure out what this is. 2 to the 6 times 6 factorial. It's a pretty big number. Okay, and in fact, go ahead and calculate that to get an idea of, how many ways can you create a 2-cycle given these cards right here? Okay, now to get a probability though, what's the probability that we would just take these cards here and just mix and mix and mix and mix, and then, when we're done mixing, lay them out and find that they form a 2-cycle relative to card value? Well, the probability will be the number of 2 cycles that could be formed, which is what we just found. In the general case, it's 2 to the x times x factorial, divided by the total number of ways of ordering those 12 cards. Well, remember, x is 6 for us, so 2 times 6 is 12. So we would simply take the number of 2 cycles that can be formed divided by the total number of permutations of those 12 distinct cards. So that's what the blue one is here, the probability. So the probability is very, very small. As x gets big, these probabilities just head towards 0 in a big hurry. Now, we're not necessarily so focused on figuring out the probability. The probability for us is just a way to get to what we're interested in, and that is surprisal. What is the surprisal of this event? What is the surprisal associated with just mixing those 12 cards, laying them out, and finding that they're a 2-cycle? So that's what we're interested in. Well, in this series, we've been calculating surprisals, and it's always the same. It's log base 2 of 1 divided by the probability of the event occurring, which in this case just, of course, reciprocates the fraction here, the probability. So this red one, which is the one we have going up, that's shooting up over here. Let me turn off the other one from before. This is giving the surprisal values. Okay. Now from the graph, we could kind of estimate what the surprisal value is for the opening performance, where we just kind of mix those cards and then we were able to pair them up perfectly. Well, the surprisal in doing that by chance alone is going to be, so our value then would be 6 for x. Remember, x is always half the length of the entire sequence. Okay, we also call that the cycle length. Okay, so here this has this 2-cycle here that we've been using has cycle length 6. Okay, so cycle length 6. Okay, so we could kind of estimate it from here. So 6 is over here on our graph. So if you go straight up, it looks like it's going to be just over 13 bits of surprisal. Okay, so let's go ahead and take a look at our table, and then that way we can get more accurate values instead of estimating from the graph. Okay, so here is the comparison of the probability values versus the surprisal values. And once again, the probability values get small so fast that they're not all that useful. I mean, it's hard to even give physical meaning to these tiny, tiny numbers. Well, that's one of the advantages of viewing it through the lens of surprisal, because we change what were difficult to work with numbers into more manageable numbers. And so that's what the log base 2 of 1 over the probability accomplishes. That was one of the reasons that Claude Shannon came up with that formula. He was trying to give clear meaning to rare events. Okay, that was just one of many things he was trying to do. So if we want to find the surprisal value for that opening performance that we showed you, we would look up 6 for x. The surprisal value is 13.34 bits. And if you've been watching any of the videos in this series, you have some ideas as to how to interpret that. We'll go ahead and just round down to 13 bits. The interpretation we would give it is the level of surprise associated with the performance that I showed you at the beginning is the same level of surprise one would experience in watching 13 fair coins being tossed high into the air and then having that individual call heads for all of them. They're all going to land heads up. And then the coins hit the ground and eventually settle down. And it's found that each and every one of the 13 coins is heads up. Okay, so I hope that kind of gets us started. Within this video and the next two, we'll be finding the Surprisal for many of the performances that we have shown on the Hidden Structures channel. Meaning, if you know what you're looking for, you could use, let's say, this particular Desmos activity. And let's say the packet size was 16, and we were matching up card values in the end. Then you could come over here, and so 16, half of 16 is 8, so you'd look up a value of 8 for X. Come over here, the Surprisal now is 20, over 20 bits of Surprisal. Okay, and we've worked with 16 card packets before. And in fact, we've even worked with 32 card packets as far as matching things up, which would be down here, actually. 57 bits. Okay, and you may recall also another interpretation that we give to these Surprisals. I guess we could focus on the packet of size 16. 20 bits of Surprisal, you can think about it in terms of 20 coins being randomly tossed and they all land heads up, and the person predicted it beforehand. We can also interpret this as the same level of surprise you would experience randomly guessing the answers on 20 true-false questions, and then in the end, discover that you got every single one of them right. It's like acing a 20-question true-false quiz by chance alone, okay? And then, of course, if you had a packet size of 32, this is just unbelievable, right? 57, imagine 57 coins being tossed high into the air. They're all going to land heads up, and they do. So anyway, that gives you some, a feel for these Surprisals. And then you can look up on your own. I've mentioned before that most state lotteries have Surprisal values between like 20 and 25 bits, and that's based on the probability of being able to win those lotteries. So this 57 bits would be like winning a high-stakes lottery twice. Twice. And I think I've read in the news that has happened, but boy, is that unlikely. So hopefully this gives you some understanding as to how we even calculate Surprisals. And in particular, how do we find the number of 2 cycles of a certain length where we're matching up, let's say, values, or mirrored structures or AMP structures, okay? And what's interesting is if you do this, and the reason that I said all of these have the same Surprisal value, okay? So that's not clear that should be the case, by the way. Why is this exactly as likely as this one or this one here? Well, it ends up that if you actually go through the kind of thing that we were going through here for this structure and for this structure here, you get exactly the same ending expression. Now, along the way, it looks different, actually, in terms of the values and where they're being placed and so forth. But if you actually kind of follow this strategy here for mirrored structures and the same thing for AMP structures, and then rewrite that product in a similar way to what we've done here, you'll see that each one of these gives you exactly 2 to the 6 times 6 factorial. Okay, so they truly do have the same level of surprise, and they truly do have the same probability of occurring by chance alone. Okay, well, thank you for watching.